Here's the legal stuff. First thing I would say is I seriously recommend you buy this book. It's an Australian government book, and although it's written for the domestic market, everything in it still applies to the commercial or mostly to the industrial market as well. So it's a wonderful book full of information and an incredibly low price. You get it from this site, Australian government, and order it and they deliver it. I'm afraid it's not available as an ebook, or at least it wasn't when I looked. The other thing I would seriously recommend is that you join the Energy University. This is a free learning resource by Schneider Electric. You join, you basically log in, doesn't cost you anything, and there are hundreds and hundreds of online training courses. You can even pay and get yourself a qualification. But it's wonderful, and I will be referring to this quite often through all of my courses. If you come into the TAFE, you'll find all of my stuff in the shared directory in the folder called Jean. Okay, so what's HVAC? Well, what happened was the buildings got bigger and bigger, and they got taller and taller, and you couldn't just open the window to get air. We need air to breathe, and we need that air to be not too hot and not too cold. We need it to be just right. There was constant sources of heat, what we call the heat load. And those sources of heat were coming from things like the sun through windows. They also came from us. We are a massive heat load. We put out a lot of heat. And then as we start using more and more modern equipment like computers and electronics that use energy, they produce heat as well. So there is this heat load, which is going to make the room hot, which is uncomfortable, so we need some way of cooling the room. There's also a need to provide oxygen so that we can breathe and to remove carbon dioxide. So we came up with a method of supplying cool air. Supply air, basically. Normally we supply this through a duct to some sort of supply air terminal. Now bear in mind that nobody likes to have a draft on them. It makes you feel extremely uncomfortable. So when we supply the air, you can't blow it straight at the person. You want the air to travel along the ceiling and fall down the walls. So we have to have the supply air terminal is normally specially designed so that the air doesn't just blow straight at the people, straight into the room. It actually travels along the ceilings. Now, if you keep blowing air into the room, it needs to come out somewhere. In most rooms, in houses for instance, it's allowed to leak just through the space along the bottom of the doors. But in a lot of buildings, the doors are starting to be sealed. So we need some way of letting the air back out. We can't just put it in indefinitely. So we have a return air grill. In the simplest sense, this just lets into the ceiling space, and it's assumed it goes somewhere. Maybe we need to refine that a little bit, and we will have a return air duct which takes that return air and takes it away somewhere. We could even take that return air and put it back into our air conditioning system. This we call economy. And we're basically recycling the air. So we now have a choice of whether we take outside air or we take return air. When we're taking outside air, we need to make the decision, is it better to take the outside air or is it better to take return air? Generally, there is a legal requirement to supply a certain amount of fresh outside air. We call that the minimum outside air requirement. And the reason for that is because outside air, we assume, is oxygenated. Return air, on the other hand, has a high percentage of carbon dioxide. We need oxygen to breathe, otherwise, well, we die. So there is a requirement to supply a minimum outside air. The other thing to bear in mind is return air, which is air that's been breathed out, is often full of other things. It's full of carbon dioxide, it's full of moisture, it's full of farts. So it might not be a wholesome, pleasant air. Sometimes, if the return air duct is not particularly well designed, we need to give the air a little bit of encouragement to come out of the room. So we might have a return air fan drawing the air out. In order to make the selection between return air and outside air, we now need an outside air damper and a return air damper. These are louvers that are driven by actuators to open or close. Of course, if you're using outside air, then the return air still needs somewhere to go to. In this case, we put another damper out and we have another grill on the outside of the building where we exhaust or relief the air. So exhaust air or relief air is air that's blowing straight out of the building. Generally, we need some way of cooling the air that we're sending to the room, because the idea is mostly to overcome the heat load in the room. So we need to supply some sort of cooling. There's a couple of ways we can do this. One of the ways we can do this is by putting a radiator in the air conditioning system and cooling the air by cooling that radiator. We passed cold water through that radiator. We call it chilled water. Typically we're chilling the water down to about 5 or 6 degrees Celsius. And we chill the water down so that the radiator, the heat exchanger, gets cold, and then the supply air we're typically supplying at around about 12 degrees Celsius. Now, that system is removing heat from the air. So the chilled water, as it goes through the heat exchanger, heats up. We cool it using a thing called a chiller, which is a refrigerator. We need to take that heat and send it somewhere else. Normally what we do is we send that heat to a cooling tower via the condenser water system. The cooling tower generally lives on the roof of the building. There may also be a boiler, because there may be occasions when we actually need to heat the air. In Perth we only occasionally heat the air, but in other countries we heat nearly all the time. So we have a boiler which can basically, instead of cooling the coil, we heat the coil. There are systems where there's only one coil and we have an exchange mechanism, valves, which either select chilled water or heated hot water from the boiler. But it's more common to have two coils, one chilled water coil and one heated hot water coil. Generally, this ducted system is feeding much more than just one room. It's feeding a series of rooms throughout the building. There may be interior spaces, perimeter spaces or whatever, but this system is feeding a series of rooms and the return air is coming back to this system. One way of doing this is by having what we call a package unit. This is a small aircon, and instead of having chilled water or heated water, it's a refrigerative system where the refrigerative coil or the evaporator is actually within the air conditioning system. This allows, and the whole refrigerative unit and everything is packaged up together in one small unit with the condenser as well. We may be heating the air either by having a reverse cycle unit or more commonly with electric heaters. These electric heaters are either called reheaters or electric duct heaters, EDH for short. Whatever system we have, we talk about the moving air loop. This is the loop of air which is coming from outside or being returned, going to the room, going through the room, returning from the room, and going back to the air handling system, the air conditioner. Oh, by the way, at this point I should say that we call a large air conditioning unit, we generally call it an air handling unit. In older systems, we would supply 2 lots of air to each room. There would be a hot duct and a cold duct, sometimes called the hot deck and the cold deck. And then within each room, or within the ceiling of each room, there would be a thing called a mixing box. And the mixing box would select either hot air or cold air or a mixture of the two and supply that to the room. It's a fantastic system and provided really good control of the air in the room. The downside of it was, of course, that we always had a hot duct and we always had a cold duct. So the boilers ran 24/7 and every day of the year. And the chillers ran 24/7 every day of the year. So all up, it was an incredibly expensive system to run. Nobody really cared in the days when energy was cheap. But now, energy isn't cheap, and more to the point, we're trying to do things sustainably. This is an incredibly unsustainable system. It's energy intensive, and it's just bad for the environment. Another way of doing this is, another way of cooling a room is by supplying some sort of a split. We call it a split because the cooling section, it's a refrigerative system, the cooling part and the heating part, normally we call the cooling part the evaporator and the heating part the condenser, but sometimes we talk about the indoor unit and the outdoor unit. They're physically separated from each other and they're in different places. You can have a ductable split, and this is what you may have in a larger house. A ducted split, you always know it's a ducted split because it has a separate outdoor unit, hence it is split. The alternative is the window unit or the room air conditioner, the RAC. We used to call them window rattlers because they'd sit on the window and rattle the window. Lovely little system, fallen out of favour. There was always this myth that they would fall off of the window and people would be killed by falling air conditioners. I don't think that happened very often, but I guess it must have happened occasionally, otherwise the story would have disappeared. Small package units, you'll sometimes see these outside of a shop or round the back of a shop or a small office. This is it's like a kind of a larger split, I guess I'd have to say. More often than not, they duct into the building. They're kind of a halfway house between a full air handling unit and just a small aircon. If we have the evaporative coil inside of the duct itself, rather than cooling water, for instance, then we call it a direct expansion system, or DX for short. A chilled water system, on the other hand, the refrigerative system cools water to about 5 or 6 degrees Celsius, and then we pass that water around the system. Remember that water starts freezing around about 4-ish. It doesn't freeze until, well, about 0. But it starts getting kind of sluggish and thick around 4. So we don't want to get the water too cold. A very cheap and easy way of cooling air is with an evaporative cooler. This is effectively the same way as a cooling tower works, and the principle is that you pass water across a cell which is like a honeycomb of holes, and you suck air through. As the air passes the water, evaporation occurs. As evaporation occurs, as each water molecule goes from the liquid state into the vapor state, it has to absorb enough energy to satisfy the latent heat of evaporation. The only place it can absorb that energy is from the surroundings. So basically, as each molecule of water goes from the liquid state to the vapor state, the surroundings are cooled down. The temperature goes down, so it cools. This is a very cheap and easy way to cool an area. The downside of it, of course, is that it produces air which is effectively 100% humid. So it produces very humid air inside the space. The other downside is evaporation can only occur if there is somewhere for the water molecule to go to. So in other words, evaporation can only occur if we have less than, say, 100% humidity. In fact, effectively, for it to work effectively, we really need less than, say, 80% humidity. It works just fine in Perth, where our humidity is normally, on a hot day, hovering around 40–50%. If we're going to be cooling water, we use a type of refrigerative system which we call a chiller. Here's a couple of different types of chillers. The one on the left uses air-cooled condensers. The one on the right uses a water-cooled condenser, so it would need a cooling tower. We're going to be using refrigerant cooling. We're going to be using refrigerant gases. The basic principle is you take a simple molecule like methane, you strip off some of the hydrogens and you put something else on there like a chlorine or a fluorine. The criteria we had for making refrigerant gases was that they needed to be stable, they needed to be non-toxic, and as much as possible they needed to be not flammable. So we stuck with the chlorines, the fluorines, that sort of thing. The downside of this is that we created a whole bunch of molecules that were very stable and also very highly polarized. That wasn't really an issue until they got up into the upper atmosphere. In the upper atmosphere, there is this protective layer around the Earth called the ozone layer. Ozone is oxygen 3. That's oxygen where there are 3 atoms of oxygen in each molecule. It's a very unstable molecule. One of the things it does is it stops ultraviolet. It's a blanket to stop ultraviolet getting to the planet. Why do we need ultraviolet? Well, we need to stop the ultraviolet because ultraviolet is radiation is a form of radiation, and if we get hit by too much ultraviolet radiation, it tends to create mutations in our skin, and we get things like, well, skin cancer, and well, we die. So we need the ozone layer to stop the ultraviolet. When these very, very stable fridge gases got up to the upper atmosphere, because they were highly polarized, what they tended to do is they tended to pull apart the ozone. They changed it from O3 into O2. O2 doesn't stop UV. So unfortunately, the fridge gases were very bad for the ozone layer. So we've now chosen a whole new bunch of fridge gases which don't pull ozone apart, and hopefully will help preserve the world for our children. Alright, now, if we're going to be using refrigerative cooling, then what a refrigerative cooler is it basically it's a heat pump. It removes heat from one place and delivers it somewhere else. One place where we deliver that heat is a thing called the cooling tower. A cooling tower generally sits on the roof of a building. We send hot water to it, which is the heat, and that hot water is cooled in the cooling tower and becomes cooler water. The cooling tower works exactly the same as the evaporative cooler I was talking about before. Basically, water evaporates from it, and as that water evaporates, it sucks in energy from its surroundings. In other words, it cools its surroundings in order to achieve the latent heat of evaporation. So we're moving water around. We need to pump that water. We use pumps. Here's 3 different types of pump. The most common pump we use is the monoblock centrifugal pump. We're also moving air around. We need a way of moving that air around. We use ducts. There's all sorts of ducting products. Now remember that just like any fluid, air is a fluid, just like any fluid, if you put things in its way, you slow it down. So we try and make the ducts as smooth as possible. We try and make the curves as smooth as possible. Otherwise, it will be slowed down. There are other accessories. As I said before, we don't want to deliver the air straight in the face of the people in the rooms. We want the air to travel round the outsides of the room. We actually want the air to travel across the ceiling of the room and fall down the walls. We have all sorts of specialized grills and diffusers which allow us to make the air travel round the ceiling, along the ceiling I should say, rather than straight into the face of the customers. Here's some more diffusers. We use fans for delivering the air. Centrifugal fans work on the principle that they spin very fast. Air is sucked in from the middle and forced by centrifugal force to the outside. There's several different types. There's forward curved and backward curved. There's also ones which have just straight blades, which we call plug fans. Another type is the axial propeller type of fan. These are better if you want to deliver low pressure, high volume, whereas the centrifugals are better for high pressure, less volume. Before we go too much further, let's have a brief recap of the refrigeration cycle. Right, you get a closed container, half full of liquid. You stick a vacuum pump on it and you start sucking the gas out of the top. Now what happens is the pressure in the container goes down and down and down, and eventually we'll get to the vapour pressure of the liquid. Or, to put another way, boiling point is a factor of pressure, and as pressure reduces, so does boiling point reduce. So if you reduce the pressure enough, the liquid starts to boil. There it goes, boiling. Okay, now, the rules say that in order to boil, it has to have the latent heat of evaporation. So, what does the molecule do? It looks around and says, I need the latent heat of evaporation. So what it does is it says, well, my energy is made up of two parts. It's made up of latent heat and temperature. So if I need to have more latent heat, I need to have less temperature. So the temperature goes down. As the temperature goes down, it starts sucking heat in from the surrounding. It gets cold. Now we'll attach the other side of the vacuum pump to another container. Now we start to pressurize this second container. And what happens in the second container is as the pressure builds up, the gas is forced to turn into liquid, because it's pushed under the liquid surface effectively. Now the rules say if you are going from a vapor to a liquid, you have to give up your latent heat of evaporation. So the molecules give up their energy. After a while, you'd have pumped one of the containers dry and filled the other container. So we put a little bit of a pipe and a valve between the two, and now we have a cycle. This side, where the evaporation occurs, gets cold. We call that the evaporator. This side, where the the vapor is turning into liquid, that's condensing, we call that the condenser, and that side gets hot. There is a slightly more complicated refrigeration cycle called the vapor absorption cycle. This works on a slightly different principle. Same principle, really. We still have an evaporator and we still have a condenser. The big difference is that we are moving the gas around by having a second chemical which is very strongly attracted to the refrigeration gas. And that chemical is used to draw the gas out of the evaporator, and then in the condenser it separates away. And in order to get it to separate away, we actually have to add heat to the system, which we add in a separate place, just over on the right there, the high temperature generator. The vapor absorption machine is a magical machine. You put heat in and you get cold out. So it's a brilliant thing if you have waste heat. It will create cooling from waste heat. You'll see them in camping fridges where you have a little gas flame, and the gas flame creates heat, and that makes the fridge get cold. When I was talking about splits, I said that there's an indoor unit and an outdoor unit. In actual fact, we don't have to have just one indoor unit. We can have several indoor units and one outdoor unit. They can all be linked together. With modern systems, you can even have the type of system where one of the rooms is being cooled and another room is being heated. We call this variable refrigerant systems. They're becoming increasingly popular because we now have automatic valves which allow it to work really well. If we are taking in outside air, and we have to take in outside air to supply fresh oxygen to the people in the buildings, then we have to get rid of some of the return air. that return air has already been conditioned. It's already been heated or cooled. We've put energy into conditioning that air. It's a shame to waste that energy. We use heat recovery systems, like heat exchangers or a heat recovery wheel, to recover some of that energy. What a heat recovery wheel is, well, it's a large wheel that rotates very slowly. The wheel itself is made up of thousands and thousands of tiny copper pipes. The air passes through these copper pipes quite readily, but as the return air passes through, if it's cold return air, it cools the copper pipes. Then the wheel rotates, and the copper pipe goes into the outside air stream, where that cooled copper pipe then pre-cools the outside air. Very little actual air is exchanged from the return air to the supply air. What is exchanged is basically cold copper pipes. So heat recovery wheels recover the heat. They're typically running at a very high percentage efficiency, 80, even 85% efficiency, for very little energy input, only the energy for the electric motor to turn the wheel. Other systems we have are what's called thermal storage system. This is where we run the air conditioning system, maybe the chiller, we run it maybe during the night. During the night, electricity is cheaper. It's also easier to run a chiller. It's cheaper to run any air conditioning system during the night because the outside air is colder, so it runs more efficiently. Now what we do is we run it during the night and we use it to make ice or very, very cold salty water. We use salt because salt has a higher thermal capacity. So we use it to make very, very cold ice, and we store that ice. Then during the day, rather than running the chillers to cool the water, we just run the water through the ice, and that runs it, cools it. We can also do this for heating. We can actually make very, very hot, well, salt, and use that for storing heat. So this is an air handling unit. It's a large air conditioner for a building. It works exactly the same as the air conditioning on your car though. Air that is supplied to the building we call supply air. There's a supply air. We abbreviate that to SA, supply air, and we'd call the supply air temperature SAT, supply air temperature, supply air humidity SAH, and onwards like that. Okay, now the air comes back from the building, it returns, we call that the return air, and the return air is full of, well, you know, carbon dioxide, moisture and farts and that sort of stuff. That's the return air coming back from the building. We take outside air in so that people can get oxygen to breathe, and that's outside air coming from there. It's abbreviated to OA. If we're taking outside air in, we need to relieve some air. Some air needs to go out. So we have relief air. Now we abbreviate relief air to RA. We abbreviate return air to RA. It's not a problem because if you look at it, it's the same air. Sometimes we recycle the air like that. Now, where we'll always be mixing in a little bit of outside air, so we have a mix air. We have a damper. We have a set of dampers, in fact, 3 dampers. We have a relief air damper. So, our present story is ended.